All right, so I didn't quite finish problem 4, part C. So there's the last part of part C says, how long does it take the moon to move a distance equal to its own diameter? So it turns out we've already done this, or we've done part of it. It turns out that the moon, the angular diameter of the moon, is about half a degree, or about 30 arc minutes. Okay, so if we already know that, right, if you know that the moon is 30 arc minutes, and you use the information that you got from part B, for example, we already worked this out, it turns out that in 1 minute, the moon, remember this was what for part B, here, let me write this down. So in 1 minute, the moon moved 15 arc minutes. Okay. So to get to 30 arc minutes, we'd multiply that by 2. So if it took 1 minute to get to for 15 arc minutes, it would take 2 minutes to get to 30 arc minutes. All right. So the answer to the very, very last part of part C would just be 2 minutes, because they really want the time for the moon to move its one of its diameters. All right. So let's move on to problem 5. All right, so problem 5. All right, so here, let me pause this and let me write it up. Pause. All right, so here's problem 5, or the introduction to problem 5. I would strongly suggest you take a look at some of these examples starting in our e-text on page 25 of our e-text about parallax. But I'm going to work this with you. So the general equation is D is equal to 180 times the baseline. That's supposed to be parentheses right there. It doesn't really look like it. Here, let me rewrite it. So it's 180 times the baseline divided by pi times the parallax. All right, where D is the distance, B is the baseline, and P is the parallax. And the parallax has to be in degrees. The thing about the units, for the distance and the baseline, they must be in the same units. Okay, so both of these, the distance and the baseline, must be in the same units. Very typically, if you're dealing with the solar system, objects in the solar system, or just even on Earth, we tend to use kilometers. Kilometers, or astronomical units are used. AU, where 1 astronomical unit is the distance between the Earth and the Sun. When you get out into interstellar space, typically, of course, you'll use light years. You can also use, well, you see, the thing is, the baseline, you can't have light years for the baseline. So here, let's actually cross that out. Very typically, we'll use a baseline of 2 astronomical units for stellar objects. We'll get more into this later. But for things on Earth, we tend to use kilometers as our baseline. All right, as our example shows. Okay, so let's do some of these problems. All right, so just remember this formula. Okay, so the distance is equal to 180. It's actually 180 degrees. The degrees cancels that's why the parallax has to be in degrees. The baseline generally is going to be in kilometers. It could also be in astronomical units, and of course pi is just a number. All right, so let's get to the very first one. All right, here we go. The first one, this is, actually, there's just three parts to it. For all three, the baseline is 1,000 kilometers. All right. And so one of the things that I want you to notice is that as the parallax gets smaller, you think about what happens to the distance of the object. Okay, so we'll I mean, if you just look at this equation, right, the distance is equal to 180, that's a 180 times times the baseline. You don't really need parentheses here. I just like to emphasize it. Divided by pi, and also divided by the parallax. So as the parallax gets smaller, the distance will get larger. All right, as you'll see. All right, so let's do the first one. The first one, they tell us that this is for part A. For part A, they say, okay, what if you know, you use this baseline of 1,000 kilometers and you measure the parallax, and the parallax turns out to be 1 degree. All right, 1 degree. Remember, degree, you can either write you know, this abbreviation, or you can use this little symbol right here for degree. All right, so let's just plug this in, and we'll see what the distance is. So the distance for part A is equal to, so it's going to be 180 times our baseline, which in this case is 1,000 kilometers. All right, so that has to be measured very, very carefully. And divided by pi, and this pi goes in the denominator, and also the 1 degree. 1 degree goes in the denominator as well. All right, so and just emphasize that. All right, so that turns out to be, let's see, what did I get? 57,295, 50, where's the 7? It didn't look like a 7. 57,295.8 kilometers. All right, so there's our part A. All right, then the next, you know, all we're going to do is we're going to make this, we're going to make the angle smaller. Okay, so the parallax is going to be smaller. And so let's see what happens to our distance. All right. So you should remember, you should see, according to the equation, the distance should get greater as the parallax gets smaller. So for part B of this one, it says, what if it was 1, and this hash mark right here in astronomy means 1 arc minute. 1 arc minute. All right, and so we know what that is, right? One arc minute is 1/60th of a degree. I mean, you could do a conversion if you wanted to. Here's a conversion, since I'm thinking about it right now. So we know that in 1 degree there are 60 arc minutes. Right. Remember, arc minutes are units of angle, right? So the arc minutes cancel, so it's just 1 divided by 60, and so that 1 divided by 60 turns out to be, in decimal, approximately 0.0167 degrees. That's a 7. All right, and so let's get back to our formula. The distance is equal to, so if you know the parallax and you know the baseline, it's going to be 180, right? 180 times our baseline in this particular example was 1,000 kilometers. All right, practice this. Try this on your own. Make sure you get the same numbers that I'm getting with your calculator. All right, and then in this particular case, we will use this 0.0167 as our parallax, right? Because that's 1 arc. That's 1 arc minute. And so remember, the last one was like 57,000 kilometers. So now it jumps up to 3.44 times 10 to the 6th power. So over 6 million kilometers. So that holds true, right? The angle got smaller, right? We turned from 1 degree to 1/60th of a degree, and the distance became much larger. All right, let's keep moving here, and so we'll do part C. Here's part C. So as you might imagine, now what we're going to do is we're going to use a parallax equal to 1, and the double hash mark means arc seconds. All right, so let's convert one arc second. All right, we'll first convert it to arc minutes. So we know that there are 60. I'll just use the hash marks, the double hash marks. 60 is 1 arc minute. So that is 60 arc seconds is 1 arc minute. And so the double hash marks cancel, if you will. You could have written arc seconds, and that would be the same thing. And then so we know that in 1 degree there are 60 arc minutes, so a single hash mark there. Now the single hash mark, of course, cancels, and so you basically take 1 divided by 60 squared. All right, and that turns out to be a very small number. It would be like this. It would be about 1. If 60 squared turns out to be is about 3. Not about. It's exactly 3,600. All right. So it's that fraction of a degree. So in decimal form, it's something like 2.78 times 10 to the minus 4th. Times 10 to the minus 4th. Of course, it's degrees, right? Degrees. All right. So let's finally do this one. The distance is going to equal 180. Sorry, that 180 times our baseline, which was very consistent for this particular problem, 1,000 kilometers, divided by pi, and then divided by 1 arc second. But that arc second has to be changed into decimal form. So that would be 2.7, 2.78 times 10 to the minus 4th. All right, and that turns out to be a distance of 2.06 times 10 to the 8th kilometers. All right. So when you reduce it, when the parallax reduces to 1 arc second, remember that you can't see 1 arc second with the unaided eye. You need a telescope to be able to see that. All right, I'm going to set up the next problem. All right, so this is problem number 6. It tells us that Venus has an angular diameter, as of course seen from the Earth, of 55 arc seconds. Right, that's the double hash mark. What is its actual diameter? And so it's kind of like the parallax equation, where the diameter here turns out to be what we call the baseline, and the angular diameter was kind of like what the parallax was. Anyhow, so if we know the distance and we know the angular diameter, we can tell how big the object is. All right, so let's go ahead and solve this. All right, so in the problem they give us that it's 55 arc seconds. Now we got to change the angle. Of course, the angle has to be in our equation. The angle has to be in degrees. So we divide by 60. We divide by 60 again, and so that it would be this many degrees, right? So 0.01527, and then it repeats degrees. All right, so we put that in our equation. That goes right here, degrees. And so the diameter of Venus turns out to be pi times the distance to Venus, which was given to us in the problem, was 4.5 times 10 to the 7th kilometers. And then you multiply it times the angle, and you get 12,000. kilometers.